So let's study Green's theorem here, which is going to help our integration of line integrals a lot simpler. So basically what it says is that you've got a positively oriented curve around a region, and it's simple, so it doesn't cross itself, right? Okay, it doesn't cross itself. It's closed, so it's not open, so it doesn't just have like that. Just not open, it's got to be closed. Also, it's what else is piecewise smooth? Yeah, that's right, piecewise smooth. So the curve in the region is piecewise smooth. So even if it has a little kink in it, like that, or like this, or like that, a bunch of kinks in it, it's piecewise smooth. We can split it up into sections that are smooth itself and evaluate those all of those separately. It's piecewise smooth, it's simple, it's closed, and it surrounds a region. It's closed, and so the region inside we're going to call D. All right, that's what we're looking at. It's positively oriented. That means that as you walk along the curve, the region is to your left. Okay, as you walk along the curve, the region is to your left. Later on, we're going to get to regions with holes. So you're going to have a region like this, and then there's going to be a hole inside. So you still have to go in a positively oriented direction. So what we're going to do in order to evaluate Green's theorem around this is we're going to cheat a little bit, and we're going to create a little bridge here and here. And so when you go around the region, you're going to go up this way and then this way along the inside curve here. And what's going to happen is you still want your region to be on the left, okay? So region on left implies C is positive, positively oriented curve. Anyway, so don't worry about this too much. We'll get to that in a minute. The point is this: if you want to find the line integral, and the integral is over C, and C has these features, all these features up here that we've been talking about. It's simple, closed, oriented, positively oriented, and piecewise smooth. Then what Green's theorem says is that you can actually look in the region inside of the curve and evaluate your line integral that way instead, using this new formula. All right. So basically what we're saying here is you have a curve in space. I'll use red. This is my curve in space. It's positively oriented. It's closed. It's simple because it doesn't cross itself. All right. And then the inside region we're going to call D. So all of this is D. The Green's theorem says the following. So here's Green's. It says when you do this line integral p dx plus q dy, which, by the way, there's two ways that we've looked at this. We've looked at it using the line integral like for density, f of x, y, ds, where this ds was sometimes written dx over dt, quantity squared, plus dy over dt, quantity squared. Okay, so this was one way that p dx plus q dy was expressed. The other way was using, now this is over C, the other way was in terms of work, where we have a vector field, and they are both called line integrals. They are both line integrals. They both reduce to the same thing. Let me differentiate between these a little bit. Let me erase this so I have a little bit of room. The integral f of xy ds, that's like if you have in space, you have a curve, and this curve has the feature where there's a function defined on it everywhere, and you're just adding up all the function values on it. The other one over here with this vector field is you still have the same curve, and you still have these points on it, but these points are um, uh, the line integral dotted, it's the vector field dotted with the tangent of the curve everywhere. So essentially, I'll do the vector field in green. So you have this green vector field going through everywhere. I don't know how it looks. Maybe it looks this way sometimes too, like this, whatever. And then those blue dots are going to be the vector field dotted with the tangent lines everywhere, tangent lines everywhere. And so that's how you're going to get, that's why this one's often in terms of, uh, this one's often the line integral for work, all right? But regardless of how you look at the line integral, what this book does and what many books do is they rewrite it like this, where your f is p comma q in this case, and then this f of x y is just different for each one of these, and you're just integrating along x and then integrating along y. This is really just shorthand for these two. Um, And I mean, I don't want to get too deep into it, but that's what's going on. So the bottom line is this. What Green's theorem says is if you want to calculate this, you can use the region inside instead of the curve itself. So it says this. It says p dx, so the line integral, q dy, over c is equal to the double integral of the partial of q with respect to x minus the partial of p with respect to y. Right? And then dA, yes. So the dA here is a little area piece of the region D. So essentially what you're doing is you have your curve. You want to find the line integral around the curve, whether that's the work done by a vector field, or maybe you have a density function. So you have the work done by the vector field f going through it, whatever, or you have a density function, little f, that's working on the curve. Maybe this is a wire or something. So it says the line integral here is equal to the double integral over this region D inside. This dA piece, remember, is a little piece of it, right? When you split it up into crosshatches, right, to perform it. And so you just do this little formula here, partial q with respect to x minus partial p with respect to y instead. So you're working on the interior of the curve, right, the region that's bounded by the curve, instead of around the curve itself. So there's a really cool way to show you this. I'm going to grab a problem and come right back. So here's the problem. This is similar to what you'll see in the WebAssign homework. It says find this line integral, we use black. The integral over c, this symbol right here that you're seeing here, that is saying that c is positively oriented. So the line integral is x squared plus y squared dx plus xy dy. All right. We're going to calculate this line integral, and c is consisting of the arc of the parabola y squared from 0, 0 to 1, 1. So here it is, 0, 0 to 1, 1. That's a parabola. And then the line segments from 1, 1 to 0, 1, so this way, and then from 0, 1 to 0, 0, and then, so now it's going down this way. So the curve is going like this. Now, if we were to calculate this, we would use a line integral, just like you know from before. You'd have to split this up into 3 different segments, C1, C2, and C3. And so in order to do this integral, you go integral over C1, and then all this mess. I don't know, let's call this, I don't know, capital M. So capital M plus integral C2, capital M plus integral over C3, capital M here, the whole integral business there. And so we'd have to parameterize all these. So you can do this like C1, in order to do this first one here, C1 would be, the parameterization would be R of t equals, well, you can do R of x actually. R of x is x comma x squared. And then you just calculate these two. Or what you can do even, which might be even easier, it's just r of t is equal to t and then t squared, like that. Yeah, so I want to keep this consistent along the whole curves. So I'll use this parameterization. Remember, this was it was the parabola y equal x squared. So I'm going to call it xt, and then y is going to be t squared. So whenever I compute this this line integral here, then I'm going to use my new parameterization for c1. So the integral over c1 will be 0 to 1. Remember, this is going from 0, 0 to 1, 1. So it goes from 0 to 1. The t's do. You can check that parameterization if you want. X squared is t squared. Y squared is t squared squared, which is t to the fourth. I'm just looking up here. And then dx will be that'll be 1, and then dt times 1 dt, plus xy will be t times t squared, and then dy will be 2t dt, like that. All right, and so when we calculate this out, so I'm going to pause the video and calculate. All right, so I worked it out. So you may want to pause the video and see what the work was there. Okay, so now I'm going to do it over C2. So C2, and so now I need to parameterize C2. So I'm going from 1, 1 to, looks like I'm going from 1, 1 to 0, 1. Yes. So I'm going to use my parameterization. So now we're going to do C2, and we're going from 1, 1 to 0, 1. Let's go ahead and parameterize that using our good old friend r of t. So r of t is it's going to be r naught plus tv, like this. So the v we're going to get from these two. So v will be, let's see, I do the x's 0 minus 1, and then the y's 1 minus 1. So that is negative 1 comma 0, like that. And so r of t will be the r naught, which I'm starting at 1, 1, plus t times negative 1, 0. So I get 1 minus t comma 1, looks like. Yeah, so it's r of t. So I have my x and I have my y. So that integral is x squared, y squared, xy. So the integral we're looking at is integral x squared, y squared, dx plus xy dy. So this will equal integral 0 to 1. This is over C2 here. So integral 0 to 1. And you can check that this is, whenever you use this formula here, t always goes from 0 to 1. That. All right, so then x squared would be 1 minus t quantity squared. Dx is going, and now dy, sorry, y squared. Y squared is just 1. And then dx would be negative 1, and then dt. So now I'm working on this. Xy will be 1 minus t times 1, and then dy. Well, the y is 1, so the derivative of 1 with respect to y is 0, dt. So this whole piece is 0. So now I'm going to take care of this, and I'm going to pause the video, come back. So I got negative 1/3 right there. So now we look at C3. So C3 is this one here. So we're going from 0, 1 to 0, 0. So now we parameterize C3. So C3, let's parameterize C3. Let me use red. So C3 goes from 0, 1 to 0, 0, 0, 0. So my V will be, okay, difference in the X's and then difference in the Y's. So I get R of T is, let's see here, R naught. So that would be 0, 1 plus T times 0, negative 1. Of course, I'm using my good old friend, this guy from way back. Seems like years ago. So now this is 0, comma 1 minus t. And then whenever I do that integration, I'll go ahead and pause the video and come back. So it looks like we get 0 for that one, which is kind of cool. So we get negative 1/3, we get 0, and we got 19 over 35. So when you do 19 over 35 minus 1 over 3 plus 0, we get 19 times 3 is 57, I think, right? 19, 3, 7, so yeah, 57 minus 35 all over 105. And so I think that's 22 over 105. Yeah, 22 over 105. So that's if you do it directly, just using line integrals like from 16.2. This is like 16.2, just regular line integrals. Now what we're going to use is Green's theorem, and Green's theorem is going to allow us to just integrate on the interior. So we're going to take this, and let's see if we get the same answer. I'll just do it to the right over here. So now using Green's. So now I use Green's. And we know, so Green's theorem. Now I'm not going to prove this. This is proved in the book. We can say double integral partial q with respect to x minus partial p with respect to y dA over d. So it was, the original problem was integral over c x squared y squared dx plus xy dy. So this piece here is p, and this piece here is the q. So the partial of q with respect to x minus the partial of p with respect to y. Q with respect to x will be y, and p with respect to y will be times 2x squared y. So we get 2x squared y squared, like that. All right, it's minus, sorry, minus, 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 I'm screwing this up. It's y, and then minus partial p with respect to y will be 2x squared y squared, like that. Sorry, not the squared. Okay, so here we go. So we're going to take the double integral of this, double integral of y minus 2x squared y, and this is dA over d. Now let's look at d. So d was this parabola, and then it was this line, and then this line here. So this was y equals x squared, and when we integrate over that, it looks like we're just going to get, let's see, this is equal to integral, x goes from 0 to 1, y goes from x squared to 1. Remember, this puppy right here is y equals 1, because this is 1, 1 here. So now this is y minus 2x squared y, and then dy dx, like that. So when we do this integration, tell you what, I'll pause the video and do it. All right, so I ended up getting the same answer, 22 over 105. So let me just walk through some of the math a little bit. So we started out with this integral right here, and we are integrating from x squared to 1, from x squared to 1 in the y direction, and in the x direction, it's from 0 to 1, like that. So I'll walk through it and go through and through and through and through. It was just simple Cal 1, basically. And I get 22 over 105. So you can pause the video and look at the math if you want. But what we got before was 22 over 105. Now, if you look at the math, compare the sides, all of this right here is the long way, and then this is Green's theorem here. So Green's is much shorter. So it's to your advantage to use it whenever you can. And on the final or on your next test, whatever, I'm not going to tell you which one to use. You choose whichever one you want. So you have some problems in the homework with this. Let me see. There was one problem in the homework. I think that was directly. It was, yeah, let's try it. This is number 9 in the homework. Number 9 in the homework. So let me pull this over and let's start it. All right, so this is the problem. I went ahead and drew it. So here we are. Let's see here. So essentially what's happening is a particle is going from -2, 0 along the x-axis, and then it moves from all the way from -20 to 20, and then it moves along this semicircle like this. The semicircle is given by this. The circle is x squared plus y squared equals 4. And so it's a semicircle. And so we need to find the work done by the force f of xy. So I'll do that. Let's use green for the force. F of xy is 9xy. I'm sorry, 9x, comma, and then x cubed plus 3xy squared. So if we were to do this directly, we would have to split the curve up into two curves, C1 and then C2. We'd have to parameterize C1 using this R of t business that we used before, R naught plus TV, and then that would be C1. And then C2, we'd have to parameterize the circle using our good old friend 2 cosine t, 2 sine t, like that, and work it out that way. I'm not going to do it the long way this time. I'm going to use Green's theorem. So in order to use Green's theorem, the work done here, this will be integral f dot dr over c, which you would normally do it. So here we go. So it's going to be, normally the long way would be to do f of r of t, r of t, and then you dot that with r prime of t, and then dt like that, over c. And so you would have to do this for two separate times, over c1, so over c1, and then over c2, like that. You would do two separate integrals like this. So if with Green's, we're going to call this p and this q, that's for f. So Green says, instead of doing all that, I'm going to use the interior of that disk, this disk right here. I'm going to use the interior instead. So here we go. So partial q with respect to x is equal to, I'm looking at q up here. So with respect to x is 3x squared plus 3y squared. And then now this is partial of p with respect to y is 9. So we do double integral, partial q with respect to x, 3x squared plus 3y squared. And then partial p with respect to y is, oh, with respect to y, it's not 9, it's 0. 0. Yes, so here we go. So this is dA over that circle, semicircle D. So the semicircle is this, it's x squared plus y squared equals 4, where y is greater than or equal to 0. Oh, this is perfect polar coordinates right here. So you're going to switch all this to polar coordinates. This is r squared and then r d theta. Theta goes from 0 to pi to 0 to pi, right? 0 to pi, 0 to pi, right? And then r goes from 0 to 2. So this shouldn't be that bad. It's going to be 3 pi, and then we're going to do r. This is r cubed, so it's going to be 1 over 4 r to the 4th from 0 to 2. So now this is 3 pi times 16 over 4, which is just 4, so we get 12 pi, like that. And that happens to be the answer. So much easier than doing this puppy twice with two parameterizations. So now the second one I want to do is number 11 out of WebAssign. And so I'm going to grab that and come over. All right, so this is one of the problems in the WebAssign. So pause the video if you need to read it. So what I've done, it says to graph it first. So what I've done is I've taken Wolfram Alpha and I've graphed it here. There's Wolfram Alpha graphing it right here. And notice that I used the word plot there. Let me do a little screen sketch here. I use the word plot here. And what happens is it plots it like that. It plots them both separately, like that, right? So I think they're kind of cool, actually. This is plots like this are used a lot in electromagnetism. But it's a parametric set, right? So instead of doing that, what you should probably do is see what WebAssign will do is they'll plot that, but then they'll say, well, maybe they thought it was a parametric plot instead. Parametric, right there. So, and this is actually what it looks like. So if instead you will just put in parametric plot, see parametric plot, and just do that directly, then it will plot it as a parametric set instead, like that. Anyway, so that's what it looks like. All right, so let me take this away, and let's just do the problem. It says, and I'll let you study what all this is here. I just want to do the actual problem. Fixed point P traces out a curve called epicycloid. Graph the epicycloid. Okay, so once you're done graphing it, what it says next to do is to, let me look at my other screen. It says, use one of the formulas. It says use one of these formulas to find the area that it encloses. So what they're asking us to do is find the area inside of this thing, all right? Now, what we can do, obviously, is split it up and just find the area here and multiply times 4, all right? So we'll do that, but we're going to use Green's to help us out here. So what Green's theorem says is, let's just take this, and let's just suppose we're trying to find the line integral around this curve. Instead of the area, just find the line integral. So what Green's theorem says, instead of doing the line integral around that, just find the area inside, not the area inside, just apply this partial q with respect to x minus partial p with respect to y, the double integral of that, dA over d, just do that instead. Okay, now this can go the other way. If you're finding the area, so let's erase this. So if you want to find the area inside of a curve, remember what we did before in a previous section was I wanted to find the area inside a region. What you can do is you can find the double integral over d, d is the region, of 1 dA, and this is the area inside that curve. If you need explanation of this, just email me as to why, what's going on there. So if this is a 1 and we're trying to use Green's theorem, then that means that this partial q with respect to x minus partial, let me make that a partial p with respect to y is just 1. So that would imply that q, there's 3 cases. One case is that q is x and p is 0. So out of this partial q with respect to x is 1, and partial p with respect to y is 0. You get 1 minus 0 is 1. So if q is x and p is 0, then this double integral, we have double integral partial q with respect to x minus partial p with respect to y is integral p dx plus q dy over c. This is over d. This is dA here. Well, partial q with respect to x is 1, so this all reduces down to 1. And now this piece here, q is x, so we get x dy. P is 0, 0 dx. So we get this double integral of 1 dA over d is just the integral x dy over c. So here's the deal. We know that this here is the area of d. Instead of doing that double integral, I can find it using the line integral instead. So this is kind of cool, I think. What it says is, I want to find this area inside here. Well, I'm not going to worry about going inside. I'm going to go around the boundary of the region instead and use a line integral. And that'll give me my area. All right? And so I'm not going to do this problem. That's just a setup for it. All right? And this is basically all you need to know for Green's theorem in section 16.4.